When you look at a symbol on the periodic table, for instance, lithium, which again I'm going to continue to go back to, we saw 3 Li 6.94. Okay. You generally, what we did earlier was we rounded that up to 7. We didn't have 6.94. But what gives with that 6.94? That 6.94 reflects what is known as the weighted average for average atomic mass. Okay, elements naturally occur as a mixture of isotopes. To use an accurate mass for an element, we have to account for how often each isotope naturally occurs in a given sample. So what that means is this number, it's actually kind of a reflection of Li with, I'm not going to say protons or neutrons. Instead, I'm just going to focus on, protons or electrons. I'm just going to focus on neutrons. The abundance of Li with 4 neutrons and the abundance of Li with 3 neutrons. So we have both of these different isotopes that are present in nature. The question is, well, is this 99.999% of all of the lithium, and this would be 0.01%? Or what is that exactly? Well, we use this weighted average to determine basically what that abundance is, or well, it's observed in nature what the abundance of those are, and then that information is used to calculate the average atomic mass. So this is displayed as average atomic mass is equal to the sum of all of the isotopes when you take the decimal abundance times your isotopic mass. And I know that I talked about this in the math review, and I just wanted to bring it back here because it's going to be particularly helpful now. Okay, so I think it's best to go ahead and tackle some example problems. So this average atomic mass of silicon. Silicon naturally occurs as a mixture of 3 isotopes. What is the average atomic mass for each of these silicon? So you have an abundance and you have the mass. You are looking for an average, but that average is going to be reflective of the abundance. So you can't simply add up those 3 masses and divide by 3. Instead, what you do is you take these percentages and convert them to decimals. So I'm going to say 0.92230, 0.04683, and 0.03087. Okay. Now those are my decimal abundances, and I'm going to say, well, I need to take this, I'm going to put this in parentheses, and multiply it by my mass, 27.977. And I use this mass because this tells me the precise mass of that isotope rather than this rounded number 28. Okay, so I want to take that abundance, or decimal abundance, multiply it by that mass in atomic mass units. Then I want to do the same thing with this 28.976, and I want to do this with this last isotope, which is 29.974. And I'm going to take all these numbers, and I'm going to say plus, plus, and then I'm just going to say equals. So I'll punch into my calculator, which my calculator is right here, lo and behold. I'm going to say 0.92230 times 27.977. Then I'm going to, that adds up, or sorry, that multiplies out to be 25.8031871. And remember what I said about significant figures while you're doing the addition, or while you're working through the process. I just include all my significant figures. But we will have to come back to significant figures after a little while. Okay, so 0.04683 times 28.976. And that's right. And this is going to be, well, 1.3569468. And then finally, this last number is going to be 0.03087 times 29.974 equals 0.9252973.8. Okay, so I have these numbers, they're kind of all over the place, but I'm going to add them up now. I've got 25.8031871 plus 1.35694,608 plus 0.9252973.8 equals. And this gives me 28.08543056. Sorry for kind of jumping all over the place, but that's the number that I get. And my units for this are going to be AMU. But is this the right answer? This is not the right answer. It's close, but it's not the right answer. What I need to do is I need to account for significant figures. We had multiplication and division involved, or multiplication and addition involved. Now, for the multiplication, we care about the fewest number of significant figures. That would be these two numbers right here. Those are going to influence, and that's got a total of 4 sig figs. So that 4 sig figs there is going to be, sorry, we got 4 sig figs there, and then our answer here, we've got 5 sig figs. So we have 5 sig figs plus, and here we're talking about 4 sig figs plus 4 sig figs, and I'm not adding all that up. I'm just saying you've got a number with 5 sig figs plus 4 sig figs plus 4 sig figs. But whenever you're doing addition, what do you care about? You care about the number of decimal places. Well, all 3 of these numbers have 3 decimal places. So we don't care about the total number of sig figs at this point in time, so we can cancel and cancel. And so we can come up with an answer that has 5 sig figs. So I'm going to say 28.085 AMU is our final answer for that. All right. Now, cerium naturally occurs as a mixture of 4 isotopes. Which isotope has the largest abundance? Okay, so cerium. So another way to look at this sort of question would be to do basically the opposite. This tells us we have boron. And this question actually requires a little bit of outside information. And I can get that outside information from the periodic table that I pulled up on p-table. Boron has an average atomic mass of 10.81. Okay, now what this tells us is we've got 10.81 is equal to 0.801, our percentage, times our mass, which is x, because we don't know that, that's what this is, plus our percentage, 0.199, times 10.013. Okay, so now to solve this, it seems like it might be a little bit tricky, but we're going to work through the entire process. The first thing that we're going to do is we're going to take our known mass and known abundance. So I'm going to say 10.013 times 0.199. I've converted that abundance percentage into a decimal. And this gives me 1.992587. What I'm going to do with that is I'm going to subtract that from both sides. So now I've got 10.81 minus 1.992587. And that's going to be, 1.99, that's going to be 8.817413. That is equal to 0.801x. Okay, so now all that I need to do is just a little bit of algebra. Divide each side by 0.801, and that gives us 8.817413 over 0.801 is equal to x. So 8.817413 divided by 0.801 equals 11.008. Okay, I do have to worry about my significant figures. Let's see, where does that come into play? We've got multiplication, we've got 3 sig figs, 3 sig figs, or sorry, we got 3 sig figs and this would be 5 sig figs. So we're down to 3 sig figs based on that number. So what that's going to do is we need to come up with a number that gives us, well, 3 significant figures, and that 3 significant figures, we can scribble those out. 11.0 AMU is the correct answer. I hope that this was helpful. This is not the most trivial sort of problem. These are kind of tricky, so definitely make sure you practice on them. All right, well, have a good one.